Hello, Mechanics of Materials students. This is our second to the last lecture on the topic of beams. So far we've done a review of normal, shear, and bending forces internal in a beam as a function of our position along the beam. We've looked at longitudinal stresses that arise due to flexure or bending. We've looked at displacement and angular changes due to that same flexure that caused the longitudinal stresses. Now we're going to literally turn 90 degrees and look at what is going on in terms of shear stresses. So this is harkening back to our big V as a function of X along the beam, which is our shear force. Basically, we're looking now at forces perpendicular to the direction of a position along the beam or parallel to a cut face that we would make if we're analyzing the beam. And just as an aside and maybe a look ahead, we are going to be making liberal use of the symmetry of our stress tensor. So remember how tau xy equals tau yx in our stress tensor. So the shear stress on the x face in the y direction has to be the same as the shear stress on the y face in the x direction. So we're going to be doing a lot of cutting of beams in different directions as we go through our derivation of expressions, and then we're going to quite literally turn those 90 degrees and say, aha, that shear stress, when we look at a corner where those two different cut surfaces intersect, they have to be the same there by the symmetry of the stress tensor. So we may use a different cut surface to derive an expression and then literally turn it on its side and say, symmetry of the stress tensor, it has to be the same here on the cut face, and then that cut face that we've related to will be what we use to relate shear in maybe a more applied sense. So we'll see that as we go along. So just going to start following from the notes here. So far we've dealt with axial stresses, longitudinal, normal stresses in the direction of the beam axis, and we've also looked at the displacements in the y direction, but they're arising from stresses and deflections longitudinal. So now we're going to look at shear. So here's basically an example of a distribution of shear forces and stresses along the cut face. We've got our big Vx, so that's reminding us that the total shear force due to the shear stresses distributed over the face. So if we integrated our tau xy all over this area, we integrated tau xy, we give it a negative sign because we've got the tau's going in this direction, in the positive y direction. If we integrated over the whole face, we'd get our shear force at that x location. So everything's specific to this one x location, this cut location on the beam. May not be so apparent, but these arrows are not all the same length, and that's meant to remind us that the shear stresses, our tau, isn't necessarily uniform over that whole face, and in fact it can't be. And here's why. As you get up to this edge, let's invoke the symmetry of the stress tensor. So these little taus have to be the same as these little taus. Symmetry of the stress tensor, right? So tau xy has to be equal to tau yx, except there's no force being applied to what is effectively the yz face. There's nothing to give us any stress. It's basically, if you look at this particular face, the stress, there's only stress parallel to this face. We don't have any kind of V on this surface. No. So basically when we're comparing the magnitude of tau xy as we get right up to this edge, it has to drop to 0. So if we were going to kind of look at maybe a little graph here of if we go in the y direction and we're going to plot tau xy magnitude, I'm kind of freehanding this. We'll go with absolute value. It's going to be 0 up here at that y. And then it's going to have to get fairly big, and then it's going to drop to 0 again on this bottom face because again, the bottom underside of the beam, there's nothing to exert shear force. So tau is going to have to be 0 right at that corner in order to satisfy the stress tensor symmetry. So the total area under this curve here, basically, if we average that over the whole area, has to give us V. If it's 0 at the ends, it's got to be bigger than the average in the middle. So that's just something to bear in mind as we go along, that we're going to have to get that match at the corners. So we're going to be able to relate our average on any one face to an average on a face that's orthogonal. So we're going to go xy, yx, xz, zx as we go through our derivation. Okay, and so this is another simpler kind of graphic reminding us that at point Q, our tau xy has to equal our tau yx, and tau yx is 0. So shear stresses right at that little corner would both have to disappear, and shears down in the middle of the beam have to be much bigger than the average in order to all add up to our big V shear force when we integrate over the area. Okay, so how do we relate shear stress xy at any point on the beam? Because now we're getting a pretty good idea that this is not going to be the same at any one location on our cross section versus another. It's definitely going to vary. How do we figure out where it's maximum? How do we figure out what the average is? So to do that, we're going to make use of a cut along another plane. So we're going to come down here and we're going to look at this kind of T-shaped beam. So y is in the direction going upward, z is coming kind of out of the page, and x would be in the direction of advancement of the length of the beam. So this is x coming out here. So we're going to cut off the little shaded top of this kind of T-shaped beam, and it's got this top is now kind of a rectangular body. It's got a dimension in the z direction of t, thickness. It's going to be delta x long. We're going to, because the beam increments, so that's eventually going to get shrunk down as we look at a single location along the beam. It's being held to the rest of the beam by this plane that would be defined by delta x times t. And we could imagine that we have some internal forces keeping this shaded section from sliding off. It's also keeping it from rising up or sinking down, but we're thinking shear, it's keeping it from sliding off. So we could define a shear force in the x direction. Now we're used to thinking of shear forces in the y direction, these resulting from maybe a vertical loading of a horizontally oriented beam. Now we're looking at the other direction just for the moment. We're looking at R is the shear force that holds this shaded section onto the rest of the beam. Okay, and we could apply a force F1 and F2 to these end faces, maybe corresponding to the longitudinal stresses that we would have if we flex the beam. We're going to be yanking on it. So at those locations, we could imagine that we have forces in the x direction. We could also just be stretching it or compressing it. So we got an F1 and F2. We're going to assume for now that F1 and F2 are longitudinal forces, probably arising from flexural stresses. So think flexure formula. We got that going for F1 and F2. So obviously the beam isn't accelerating, and this little shaded section that's on top of the beam is not accelerating relative to our coordinate axis center, which, by the way, I've arbitrarily decided to situate at the centroid of the whole T cross section. It's a convenient place, especially if I'm going to apply the flexure formula later on. So I could take this rectangle, which is a shaded section, and I could put it in static equilibrium. So I could basically add up F1 in the positive x direction plus R, which is the shear force being exerted by the bottom of the T section that is below it. And I'm going to subtract F2, and that should all equal 0. I'm not going to consider anything going on in the y and z direction at this point because we really just don't have anything in the way of applied stresses. I know that R has to act over an area equal to T times delta X, and then F1 and F2 are going to act over this area A, which has a dimension T in one direction and then some y dimension in the other direction. So area A equals T times some y. Because if we want to relate stresses, we're going to have to forces, we're going to have an area. Okay, so we assume that F1 and F2 are due to moment being applied to the whole beam, so rather than just an axial stretch or compression. So we're going to drop in the flexure formula for that, and we're also going to get to the flexure formula, we're going to express force in terms of axial stress. So our sigma xx integrated over the area. So F1 is going to be our axial stress, sigma xx, at x plus delta x. So we've got F1, so basically our zero coordinate was maybe back here where F2 is. So F1 is a little more advanced down the beam, and then F2 is going to be the integral of our longitudinal stress back at x. So x, longitudinal stress at x, longitudinal stress at x plus delta x, or minus delta x. We'd end up getting the same thing. Get force from longitudinal stress by integrating over the area. We relate our longitudinal stress through the flexure formula, assuming it's coming from an applied moment on the beam. So it's just flexural stress. So we can relate sigma xx to moment of inertia, and y, so the position. Now we're talking about position on the y. So we're saying, okay, where is this little shaded slice relative to our neutral axis? And in this case, we're going to say the neutral axis is acting at the centroid of the whole beam. So we've defined 1y in this case. So we have to go back to which y are we talking about. So stress is particular to a given area. So remember, y is where are you relative to the neutral axis? It's up or down, or relative to the centroid if your neutral axis is going through your centroid, which in this case it is. So kind of putting a little note over here to remind us what y means. Okay, so the moment that we would encounter at a given position along the length of the beam, it's going to vary with the position x, but it's not going to vary with the y or z position in that cross section. It's pretty much the same over the whole cross section. It only varies with position down the beam. So we can take that out of the integral. And the moment of inertia of that cross section about its own z centroid also doesn't change with position. It's a function of the geometry of the actual cross-section shape. So m and I can come out of the integral. So we can define F1 and F2 as just our moment at one position, our moment at another position, divided by the moment of inertia of the whole cross-section times the integral of our position on that cross-section relative to its centroid, integrated over the whole area over which F1 or F2 is being applied. That's not the whole cross-section area, right? Because we're only applying, remember, this is all coming from putting this little rectangle into static equilibrium. So I'm integrating over this area A, not the whole area of the entire cross-section. So it's the area of this little top that I've whacked off, that I'm relying on shear force R to keep attached to the rest of the beam. A little thought experiment there. Okay, so now I'm going to plug these expressions for F1 and F2 back into my static equilibrium that's keeping that little top shaded slice from sliding back and forth in the x direction. And remind myself that I can also write an expression for shear force R as the average shear stress on this horizontal surface that I'm gonna make this box invisible here for the moment, and I'm gonna look inside of it. Okay, so this bottom surface here, this bottom surface where the shaded rectangle, the shaded box attaches to the rest of the beam, that's the surface over which R is acting. It has an area of delta x times t, and if we basically envisioned an average shear on that plane, that average shear tau times delta x times t would equal R. So I can express R in terms of the average shear on that plane. And just as a reminder, that plane is in the XZ direction. It's parallel to the XZ plane. But it'll have a relationship to the YZ face through our symmetry of our stress tensor. Okay, so now we can drop in our stress and area-based expressions for our forces into our conditions of equilibrium and solve for R, since that's getting us towards shear. That's what we want to know. So we can say R equals F2 minus F1. And if we take F2 minus F1 and we basically factor out this integral expression that's common to both, we get this expression in front. Remember, IZZ came out of the integral. And then we can divide by delta x. And so we get something that looks suspiciously like the definition of derivative for moment as a function of position. So basically our numerator of this fraction divided by delta x, the limit as we take delta x to 0 is dm dx. We have a 1 over moment of inertia about its z-centroid for the whole cross-sectional area times the integral of the y position of our little cut shaded top integrated over its area. And a little reminder, hey, we now have a relationship back to our shear force on the cross-section end area, because dm dx is big V. So now we're relating back to shear force, which was kind of what we were aiming at the beginning. So we're saying the shear stress, and I'm going to do a little impromptu box here just to remind us of which shears we're talking about, because this is where it's real easy to kind of lose this argument. So we are relating the shear force, and of course I got to look inside my little box again. We're relating the average shear stress on that face times this dimension, this thickness dimension on this end, to the shear force on the opposing face at 90 degrees. And so of course we're going to, in order to relate those, we're going to end up applying the stress tensor symmetry to relate the tau that's applying to this kind of horizontally oriented cut face to something where I would relate what's going on with my big V, which is going to be acting in the y direction on the x face. So if you think about it, we're going to relate some shear stress on a face that has a y surface normal that's heading in the x direction to what's going on the x face, where we're looking at a force going in the y direction. Hey, that's symmetry of the stress tensor. So we can do a tau yx, which is what this is, related to a force that originates from a tau xy. Fair enough. Okay, so now the last thing we have that's kind of hanging out there that's a little bit, less well defined is this integral of the y location of that cut shaded rectangle top that we sliced off and its end area. And how do we define that a little bit better? So we can use our definition of centroid. So we can say that our integral of y dA is going to be equal to a centroid position times the end area. And in this case, what we're looking at, this y bar, is the distance from the beam centroid to the centroid of our area A. So coming back here, if we imagine, this point maybe right here is the centroid of our area A on the end of our cut shaded area, and here's our centroid of the beam. This distance is y bar. Okay, because then that relates basically to the idea of our longitudinal stress, whence originated, our YDA. That entered our picture through the flexure formula description of axial stress, or sigma xx, and that is related to, how far up are you? So that, y is going to get bigger as we go further away from our centroid. Now, that in practice, when we start looking at the magnitude of tau average, we're going to find that things are opposite than as to how they were with our longitudinal stress. When we looked at applying a flexure, a moment to a beam, and then we looked at the cross section and said, okay, where is our maximum longitudinal stress at any point on that cross section? And we said, it's the place that's farthest from the centroid of the cross section. We've got two factors that are going to be acting on our max shear. On the one hand, we have our tau bar. So it would be easy to say, hey, we're probably going to find the max shear out at those end surfaces as well. But when we look at how we apply this little cut section, what we're going to find is, if we envisioned, okay, I want to find the shear out at this very top, I'm going to shove y bar to its maximum value. What I end up doing is creating a little teeny tiny slice up here, so area goes down. And that ends up winning out. And furthermore, we know that tau xy has to equal tau yz up at this corner. Tau xy has to equal tau yx at that corner due to the symmetry of the shear tensor, of the stress tensor for shear components, anything not on the matrix diagonal. So we know that we're going to get a minimum out there because it's 0 on the opposite face. So as it turns out, because of this area factor, we're going to find that our maximum locations on the y-axis of our beam are going to be close to the neutral axis, if not on it. So that's kind of looking ahead, and we'll show that in an example coming up. So a few definitions that you might see in different books or handbooks as you go along. What we've now defined here, basically by equating this tau, evaluating this expression, substituting in big V shear force on the cross section for dm dx, and then substituting that y bar A times the area of that shaded slice, we have a bona fide algebraic expression for average shear stress and beam dimensions, applied shear force on the cut face, so basically the x integral of our distributed load, something at the moment of inertia of the entire beam cross section, and then this distance of the centroid of our shaded section versus the centroid of the entire beam cross section, and then the area of our little shaded slice. That's the Q factor up here. And then the product of tau bar, or the average shear stress that we're going to consider at the location of interest, times the thickness, basically the dimension, in addition to our delta x that's defining our cut. This product is known as shear flow in some books, so you might see that referred to as shear flow. So if you're defining area as delta x times t, as was our case, it's pretty easy to see that T is going to cancel out of both sides and wouldn't end up being a factor. Depending on your shape, that may or may not always be the case. And as a rule of thumb, if you want to go for the location on the beam cross-section where you're going to find the maximum shear, head towards the neutral axis and go for the places where your actual thickness in the dimension of one dimension of your cut area is going to be minimum. That's a general rule. Non-intuitive, because at this point it looks like it doesn't matter because it's canceled out. Depending on the geometry, that won't always be the case. So average shear stress times our thickness that we use to define our shear cut plane is going to be equal to the shear force at that location along the beam. So now we need to know where V is a maximum, divided by the moment of inertia of the beam cross-section, times this Q factor, which is a combination of the area of our cut face that we're defining and the distance from the neutral axis. So once again, as was the case for our longitudinal stress due to flexure, a bigger moment of inertia of that cross-section is going to win. And this is moment of inertia about the z-axis, so it's that same axis, not y. So basically the same kind of shapes that would have given us effectively rigidity or lowered our axial stress, lowered our deflection. It's also going to do us some good for shear, which is probably why beams are shaped the way they are in practice if you look around. So let's do an example where we actually apply that equation. So we're given a beam cross-section, another T-shaped beam. And we're told the point of interest on the beam, we know what the shear force is 2,500 newtons. This is at a particular location along the beam. Somebody wants to know what's the average shear stress at points B and C. And so B's up here, C's down here. Now a note about average shear stress. We defined tau average in terms of that cut slice, T on one side and delta x on the other. And then we've said, well, when we did our derivation of the shear equation, we've shrunk that delta x down to nothing. So don't we have shear stress at a point now? Well, we kind of have shear stress along a line now, because remember, we didn't shrink T to 0. So what we really have done when we shrunk that delta x to 0, we got we are now looking at the average shear along the thickness line T. So it's still an average shear. So let's go ahead and look at applying our equation. So let's start with point B. We want to know what the shear is at point B. So what we're going to do is we're going to make a cut, and we're going to define, a little shaded area up here, and it would go, back in the x direction. So we got another little shaded volume that we have going. I'm going to erase the back part of that because we really don't need it, and it's interrupting some of our dimensions we need for area. So we've got a T thickness, and that's 5 millimeters. We can define the area. So the area is point is 5 millimeters times 20 millimeters. This is 20 on that side. So we can get A, 20 millimeters. And we know that the centroid of this area is halfway down its height. So the centroid is 10 millimeters from point B. And we know that the centroid of the whole cross-section, the Y centroid, is at 16.25 millimeters from the base. So basically we can do some algebra and dimension stack up and find that the distance of this little shaded area centroid to the centroid of the whole cross section, Y bar, is going to be 28.75 millimeters. So that's this Y right here. Okay, area is easy. We have 20 millimeters times I'm calling it T sub B, which is, this would be 5 millimeters. 5 millimeters. And that's going to be equal to the average shear stress at B, and that's averaged over this length of that thickness times T sub B. So, T sub B's are going to cancel in this case, and we're left with V. We can calculate the moment of inertia of the whole cross-section using method of composite parts, use the parallel axis theorem, shifting things around. We can use our knowledge of moment of inertia to get an IZZ, and that goes in here. And there we go. Solve for tau bar, and we get 9.78 megapascals, which is not as big as what we tend to see for longitudinal. Now, a note about the effect of our Y position. We see that our area is going to be a function of where B is. So say we put B like all the way down here. So we looked at this entire larger area. So basically, instead of being way up here, our Y bar would drop some. In fact, our Y bar would be at basically at 55 millimeters minus the 16.25, but our area would have gone up quite a bit. So everything on this side, this Q, would have gone up quite a bit. So we would have gotten a much bigger number here. Y bar would go down, but A would go up. So basically, if we looked at a cut plane that goes right through the neutral axis, basically our magnitude of tau xy and tau yx is maximized versus what it is further up. So let's look at what's going on at C. Now this is where we really have to think in terms of turning ourselves at right angles. We're going to make a cut at C that's basically going to be in the yx plane. But when we look at our y position of C, we're still going to reference it on the y-axis to our centroid of our entire cross-section. So even though the cut plane that we're going to relate to is in a different orientation, we're still looking at our positions on the basis of how far are they along that y-axis. So here we're going to be relying on the fact that whatever shear force is connecting this section here to the rest of the T down on the flange is going to be equal to something going on the face. So we're not slicing it all the way across the flange. We're just making a cut right through that minimum thickness at C. So I'm going to draw it thickness like that at C. Okay, so TC, thickness at C. The T bar was, cross-section was uniform, so the whole thickness was 5 millimeters, so TC equals TB, and our centroid, our Y centroid of this is going to be half of TC, so it's 2.5 millimeters. So we can think basically our Y bar in this case is going to be our 16.25 minus 0.25. Dimension part way up. So the whole one minus that dimension. And it's basically, in this case, it's going to have another sign. It's going in the, we're going downwards from our centroid position on our cross section. Okay, area. So I'm thinking a Q over here. So I got my Y bar. I got my 16.25 minus 2.5, so I got 13.75 as Y bar. The area in this case is going to equal my 10 millimeters dimension here times the whole 5 millimeters TC. Here's my same V, my same shear force that I had, 2,500 newtons, my IZZ, and that's going to be equal to the average shear stress along this line, this cut line TC, times the length of the cut line TC. So those, again, cancel, and we get an even smaller number and going in the other direction. So in this case, our area is not dependent on our particular position of where we put our cut line. So we could put our cut line out here. Our area would be smaller, definitely, but our y centroid, our y bar, wouldn't change. So I guess I should have said it opposite. Our y bar would stay constant. Our area would be decreasing. So we can imagine, not surprisingly, our shear stress is going to be smallest out here close to a free surface where we don't have any ability to apply force. I'm looking, going in the x direction, negative x direction back here. And it's going to get bigger as I move closer into the center, because even though y bar isn't changing, A is changing as I get a bigger and bigger area. So that's the area versus location factor of Q, of that Q factor. So where you put your cut, which plane you're considering, really matters, and that's not totally unlike longitudinal. So we're seeing now for both shear and longitudinal stresses, where you are in your cross-section matters. You're going to have points where things are maximized. So if you're looking at design for shear of a complicated beam, you need to look at what cut do I calculate around to make sure that I'm getting the maximum tau that I'm going to find anywhere on the beam. So one way to do that is to do some experimental cuts, move them up and down, see how they vary with position, and it's basically going to be a trade-off between your y centroid of your cut area to your y centroid of the whole cross section versus the area of your cut area. So, where's your Q maximum? It's going to be the kind of what you're going to find. And then in cases where if you have a Q that is minimally dependent on the thickness of your cut, it will always have some dependence. But if you have a more complicated shape, then you might want to just divide both sides by your thickness over in your shear flow expression and solve directly for tau bar. We're going to be looking at some pretty simple shapes. This T-bar was probably one of the more complicated ones. You could probably imagine how an I-beam would have similar trends. Right in the middle of the web and close into the center of the flanges is where we're going to see the biggest shear stresses. So a rectangle, circular cross-section where things are uniform are going to be a lot simpler for calculating Q and our cut length. Although circular cross-section, our cut length might change as we go up and down. So that might be a little more complicated. We're not at this point considering Y position variable thicknesses. So we're kind of looking at all rectangular beams for now. But if there is a Y dependence of T, as long as we know what it is, we can just toss it into our formula. So just to recap, we've selected shear planes that ensure we have a minimum thickness T. Since all other things being equal, those will lead to a maximum tau bar. In this case, there was no dependence because it canceled out of both sides out of that area expression for Q. But if that weren't the case, they would still point us to the minimum. And then more important, we found that there was some dependence with Y, mainly through area, which gave us locations on the cross-section of our maximum average shear stress. So we got a tau bar max near the neutral axis, up and down, and near the centroid of the beam as we went if we looked laterally in the z direction, right where those flanges intersected the web. So typically shear maxima, shear stress maxima is going to be close to the centroid of your cross section, and then axial or longitudinal stresses will be maximum far away in the y direction. So got to look both places when you're trying to look at the maximum stresses in a beam and do a design. So we're going to end now, but just looking at our upcoming, we have one lecture after this in the topic of beams. We're going to take a super simple beam shape, just a rectangular 2C by 2T rectangular solid beam, and we're going to apply everything we've learned so far. We're gonna solve it like a statics problem, get shear and bending as a function of x, and then we're going to look at longitudinal stress, we're going to look at deflection, and we're going to look at shear, and see what we would do if we had to design it around maximum load or yield stress or whatever, and get expressions based on geometry position of where we're going to hit our design critical points. So stay tuned for that.